So I'm recording good. So we moved up assignment 4 simply because in order to be able to have it marked and then to have you guys able to appeal your grade, we need a little bit of extra time. So yeah. I'm going to adjust it slightly. So the question is whether assignment 4 length is adjusted in terms of the, I'm going to adjust it a little bit. But yeah, you're going to have 2 weeks and 2 days instead of the usual 3 weeks. So, I'll try and take that into consideration. However, I still have to cover the material. So it's going to be, from here on out, it's going to be a dense few weeks, I guess, in terms of assessments and deliverables. So we are right here on the 13th. So you have a tutorial 4 that's, so technically we opened it up last week, but it's, it should be done sort of this week and it's due next Monday. And then you have assignment 3 that's due this weekend on Saturday again. And then next week you have a quiz, quiz 3. So yeah, because of this, because I had to push quiz 2 back a couple weeks, it's a little tight on these 2 quizzes, but they're not too long. They're only 60 minutes, if that. So you guys should be fine. I'm going to release a practice quiz probably around Wednesday. And then, assignment 3, doing assignment 3 is a great way to practice because I try and keep, so the material that's on assignment 3, I try to put that on quiz 3, et cetera, et cetera. There's some small exceptions, but in general, that's how we try and do it. And so, yeah, assignment 4 now, it was going to be due here, but instead, we're just going to give you till the end of the holiday. So just be aware that so Saturday, Sunday, and the holiday Monday, technically nobody is having office hours. I might jump in on the Discord channel and answer a few questions, but I can't guarantee anything. So nobody's scheduled. So if you have any questions, make sure you ask them during this week about assignment 4. But yeah, we'll get to that. That's sort of in the future. Okay. Any questions about the calendar, where we are, anything like that? Okay. Let's go then. So we'll jump right into the lectures. So we're looking at. Let me turn off the video. All right. So one of the things that we're looking at tonight is models of computation. Again, these slides are based on the slides of Dr. Robert Collier. I've modified them somewhat, so any mistakes you find are likely mine. So last week we talked about graph theory. We talked about subgraphs, spanning subgraphs, spanning trees, graph planarity, and graph coloring. So graph planarity means I can draw it on a piece of paper without any crossing edges. Graph coloring means I color, no 2 neighboring vertices should have the same color if I have a valid coloring. And then subgraphs is just a subset of the vertices and edges of your graph. And spanning trees are sort of the minimum number of edges you can have in a spanning subgraph, basically. And they don't have cycles. So this week we're going to talk about models of computation. So when we talk about a model of computation, we want to analyze these programs that we're going to write and these algorithms. And so what we're going to do is just sort of take a simplified version of, you could go really in depth with how long each operation is going to take, but we want to make everything simple. So we're going to sort of figure out which operations most impact performance, and then we're going to count those. So these are sort of the bottleneck operations in our algorithm. And basically the number of those is a good indication of how fast your algorithm is going to run. And then when we analyze them, we're going to analyze them using asymptotic analysis. So we're really interested in, so it's a systematic way to analyze algorithms, but we're really interested in sort of how these functions grow with the size of the input. So if you're running a program on a small input, then it almost doesn't matter what algorithm you use because everything's going to run very quickly. But as these, if you're trying to run an algorithm on a graph of 10 vertices or a graph of 10 billion vertices, well, when you're running it on 10 billion vertices, then the algorithm you use is going to matter a lot. So this is a way to analyze these algorithms and count the operations. And so we're going to put the things we learned about sigma notation, we're going to put those to use here. And we're also going to learn how to count operations using something new to us, a recurrence relation. And so that's, we count operations using recurrence relations on, when we, geez, Louise. So I'm having a brain aneurysm. But yeah, when we have recursive programs, that's it. My goodness. So this is a way to analyze recursive programs, which are actually, they can be very efficient, and they're also a nice, simple way to write a program. And we'll see all that. And then if we have time, we'll get into big O, big omega, and big theta. And that's sort of, well, these are all these three topics are related. So we'll see that, maybe. Okay, so a model of computation. An algorithm is a finite sequence of unambiguous instructions. So this is what we're going to be analyzing. Unambiguous means can be expressed or modeled discretely. Of course, we know that computers are discrete machines. So when we write a program, even the instructions have to be discrete, right? There's nothing ambiguous. A computer does exactly what it's told, and nothing else. And just as an aside, when we talk about algorithms, they're not necessarily restricted to computers, although that is where they're used most often. But any sort of discrete series of instructions, when you can express some operation that way discretely, you're essentially running an algorithm. So an example of instruction on a computer is given a state or value X, perform instruction Y. And that's basically, everything a computer does basically is read a piece of memory, maybe do some computation, and then write a piece of memory. So this, given a state or value X, perform instruction Y is basically every instruction your computer is going to do. But now we want to analyze how good an algorithm is. So how do we define good? Well, the set of solvable problems is the same on every computer, right? So in terms of, when we talk about power on computers, we're not really talking about what a computer can solve, because they can all solve the same problems. When we talk about power, what we really mean is speed, right? So when we have a more powerful computer, what we're saying is we have a faster computer. But basically, the types of problems that a supercomputer can solve is exactly the same type of problem that your phone can solve. The supercomputer is just going to be faster. So, and this also extends to algorithms. When we talk about a good algorithm, we want basically a fast algorithm. And of course, it goes without saying, we want a correct algorithm. So how are we going to measure the speed of an algorithm? So that's the big problem. And that's what that's what our model of computation encapsulates. So we could code up the algorithm, so write it in Java or Python, and then we could time the performance. And we do that quite a bit, actually. But the speed can then reflect the size of the input and the hardware. So maybe on a small input, it runs really fast, and on a large input, it runs really slow. Or maybe I have a very fast computer. But we want a way to measure algorithm efficiency without necessarily getting bogged down into all these details of what kind of hardware am I running on, or what the problem size is. So we want efficient algorithms, not necessarily tied to the context, which could make things run faster. So some operations are typically faster than others. So what we want to find basically is so addition using registers is faster than RAM. RAM is faster than disk. So these are you know, if you're running it on a supercomputer, maybe I can go to disk really quickly, but on any given computer, this operation tends to be faster than this operation, and this operation tends to be faster than this. So we can identify what the bottlenecks are in our algorithm. So we're going to select a fundamental operation or category of fundamental operations. And basically we want the worst case, right? We want the bottleneck. We want the thing that's going to slow down our algorithm the most, and one that occurs frequently. All right, and then we determine the number of times this operation occurs for a given problem size. All right, so then to sum all that up, we select model of computation as we select a fundamental operation and then determine how many times this operation occurs for a given problem size. All right, so many algorithms have an obvious fundamental operation. We're now going to see an example and try and pick out what the fundamental operation is. So we're going to examine a pair of search algorithms. And we're just going to give a very general, not even going to get into pseudocode really. We're just going to give an English description of these algorithms. So given a list of names stored in memory, sequence, we're going to find if a certain name is stored in the list. In this case, it's Jesse. Now these names are not in any particular order, so we can't utilize any sort of organized search in this case. So our algorithm is going to be basically start at the beginning of the list, compare the name that we find there to the name we're looking for. If we found it, we return true. And if we didn't find it, then we go to the next location and then we continue. And we go through the entire list. And if we find it, we return true. And if we don't, then we return false. So this is a linear search algorithm. And then another search algorithm, let's say that the list of names or the sequence of names was in alphabetical order. So now we have, now we can be a little bit smarter about how we search. So we want to find if a certain name is in this list. So what we're going to do is we're going to jump right to the middle. And we're going to see, we're going to compare the name in the middle to the name we're looking for. And if it's not equal to that, well, if it is equal to that, we return true. Otherwise, we know that the name we're looking for should be either in the first half of the list or the second half of the list. So then we're going to jump to the middle of the first half or the middle of the second half. All right. So for example, if we're searching for, so if we have this list of numbers, I'm using numbers here just because it's easier and simpler to demonstrate. And I'm searching for 18 in this sorted list, and I know they're sorted. So what I'm going to do is I'm going to start in the middle of the list, and I'm going to compare my 18 to what the number that I find there. So that's 14. And I know 18 is greater than 14. So what I'm going to do is I'm going to sort of throw away everything over here, because I know that the number I'm looking for can't possibly be there. Right? So I'm only going to look at the larger half of the list, so to speak. And then what I'm going to do is I'm going to look at the middle item there. So the second thing I look at is going to be this 21. Now I know that 18 is less than 21, so I can throw away all of these items and then strictly look at this, this again shortened list. So each time I take a step in this binary search algorithm, I basically cut my search space in half. All right, so the third item I look for is going to be the 15, and I know my 18 is greater than that, so I'm going to throw away everything here, which is simply that one number, and then finally I look at the correct location and I find it. And this is, you know, if you had well, back before everything was online, you know, you'd have a dictionary or a phone book and you would look through in alphabetical order, and you wouldn't start at the beginning, of course, you would flip through the middle and then sort of flip the approximate number of pages that you think you need to, you know, once you see where you are and see where you're supposed to be, then you can sort of jump a bunch of pages at once to try and find what you're looking for. All right, so then what is the fundamental operation in the algorithms we've discussed? So there's reasonable options is maybe comparison operation. So we're doing that quite a bit. So if we're searching for something, then we're always going to be comparing it to some item in memory, or simply memory access. So that tends to be the bottleneck in a lot of these algorithms or programs. Every time I have to go to disk, that's going to take a lot longer than if I have to do just simply a computation, like a comparison. All right, but for people who develop these sorts of algorithms, they usually look at both of these operations. But we're just going to keep it simple for now. So our model of computation will be collection access. So each time I look at my list, I'm going to count that as an operation. And then I'm going to count the number of times I have to look at my list for each of these search algorithms. All right. And so we express the time complexity of these algorithms in the number of collection accesses. So that's our model of computation. All right, and we're going to express it in terms of the problem size, and usually the problem size is denoted as n. So time complexity is a function with a domain of the problem size and a codomain of time. So we haven't actually looked at functions yet. That's coming up shortly, but so you're going to get a slight introduction to functions in this lecture, and then we're going to go into them in more detail after big O notation. So the problem size is not the only factor in algorithm speed. So sometimes the information that we're given, if we're trying to sort a list, for instance, and the list is already sorted, then our algorithm might go actually very quickly. So but we can't assume this. So we want usually examine the worst case or average case time complexity. And it's usually going to be the worst case. So we're going to assume that if we get a sequence of items and we want to sort them, we're going to assume that they're in the worst possible order for us. And if you go on to data structures, comp1805, which you should, you'll see random algorithms, and then in that case, you'll analyze their expected time. We're not going to do that in this class, but it's not the only. So worst case and average case are not the only ways to analyze these algorithms. If you use random algorithms, you will look at expected time. Okay. All right, so that's just a short little introduction to the models that we're using. So let me see here. So now we're going to go on to, these really could be the same set of slides, but this is how they're formatted, so I just kept that format. So now we're going to use those ideas in our asymptotic analysis. So the thing about these slides is generally I do these examples on the board, but I took these actually from data structures, the slides. So you're going to notice that the color scheme's a little bit different, the formatting's a little bit different. But the thing is, there's a really nice example, and I think it's well illustrated. The algorithms that we're going to look at are well illustrated in these examples, so I really wanted to use these. And apparently it's a bit of a pain to try and, or at least it's something I don't know how to do. So you're going to have red here instead of the usual green, but other than that, there's no big changes. Okay, so we're going to analyze a couple of sorting algorithms. So one of them is selection sort. And so selection sort, we find the smallest item and we swap it with the first position. Then we find the next smallest item and swap it with the second position, et cetera, until finally we have everything in the order that we want. So this may or may not make sense to you. We're going to be sorting a list. So we'll go through an example of how this works. So say we're given this unsorted list of numbers, 7, 3, 9, 8, 5, 2, 3, 1, and now we want to sort them following this algorithm. So what we're going to do is we're going to start at the beginning of the list, and then we're going to find the smallest item. So what we're going to do is we're going to examine each item in turn. So we're going to look, and we're going to remember the smallest. So in this case, right now, 3 is currently the smallest. So I looked at 7. 7 is my first. Let's go back to the beginning. So I start at 7. This will be my smallest. The next one I look at is 3. 3 is smaller than 7, so I'm going to replace the 7 with the 3. Then I'm going to look at the 9. So 9 is greater than 3, so I don't want to change what my smallest is. Then I look at the 8. 8 is still greater than 3. I look at the 5. 5 is greater than 3. I look at the 2. Now 2 is less than 3, so I'm going to put the 2 in here. And I examine the 3. And then finally I look at the 1. And then the 1 happens to be smaller than the 2. So I've gone through the entire list and I found the smallest item in that list. And then what I'm going to do is swap it with the first item. So I found the smallest and I swap it with the first item. So now you'll notice that this first item is in sorted order. It's in the place where it's supposed to be if this list was sorted. All right, so now I'm just going to do the same thing, but I'm going to do it on this shortened list. So I'm going to do it from here to here. So I start, my find smallest starts at this 3 index, and I look at each of these items in turn. And on this sweep, I find that 2 is my smallest. And so I'm going to identify that and then swap that into the next location. So now I know that my 1 and my 2 are in their proper place. Everything else might still be unsorted. Okay, so I'm going to continue. So now my next index that I point at is the 3rd place. So I want to find in essence, the 3rd smallest item in my list. So I go through them one at a time. I find that 3 is the next smallest. I swap that out. Now I look at 8. I go through the list again. I find that 3 is the smallest. So I put that into the next location. And you can see that we build a sorted list from the beginning, and then we incrementally build this sorted list. So each loop, each sweep of this list, we put one more thing in the place where it should be until we're done. And then we have a sorted list. Okay, so that's called selection sort. So is that clear? Any questions on that so far? Is everybody still following? So we want to analyze this algorithm now. So what we're going to do is we're going to, of course, have figure out what our model of computation is, and then we're going to count those operations. And so here is the pseudocode for that this selection sort. So here we go from this first for loop is the one that the first loop, it's going to put the first item in sorted order. The second loop, it's going to put the second item in sorted order. So this I points at the current location to be sorted. This next smallest index keeps track of the index of the smallest item we found so far. So on the first sweep, the index is going to be, and these will be indexed, of course, starting at 0. The way we index things in computer science is we start at 0 and go up to whatever number we need to, in this case 7. So on one sweep of this algorithm, the next smallest index, this would be equal to 7. And then, so this part is where we walk through and examine every item and find the smallest. And then we store, if we happen to be looking at something that's smaller than our current smallest, then we store the index of that item. And then when we're done, we swap that the next smallest index with our current index. We swap whatever's at this location with whatever's at this location. Okay. Good. So that's the algorithm. So you've seen the pseudocode, you've seen the English. This is going to be the thing that we're going to be analyzing. So hopefully you can see where each of these steps is occurring in this pseudocode. So a couple things I want to point out to you here. So when we talk about pseudocode, what we mean is something that this isn't an actual programming language. It's just something that could be easily converted into any programming language. So most programming languages are very similar. They differ a little bit on syntax, but not in expressiveness, generally speaking. So this represents some unnamed language. The other thing I want to draw your attention to is this sort of, when we look at these ranges. So what this means is this is going to be imitating, so if you use Python at all, you would say for I in range 0, length -1. Now in Python, what we have is we start at 0. It includes this value, but it does not include this value. So if I said something like for I in range 0 to 10, this I is going to take on the number 0, 1, 2, up to 9. All right, so it does not include this last number. So when we express these things in pseudocode, the square bracket means we include that number. That's a closed set, although that's a little bit advanced for what we're doing, but that's what it represents. And if it's a round bracket, then it does not include that last. Are you expected to know how to implement these search algorithms in pseudocode? No, not these ones per se, but you're expected to know how to analyze a piece of pseudocode. So these are going to be probably, or just express the algorithms. Yeah, so the algorithms that I'm going to give you on an assignment or a quiz are just going to be nonsense algorithms. So you're just going to have to analyze. So we're going to look at today basically how we analyze these for loops, how many times, how we count them, and how we turn all this into a sigma notation. So you don't have to memorize these algorithms. These are just examples of something, sorting occurs quite often in computer science, and it's generally this starting place of when we're looking at how we analyze algorithms. So, and these are two of the simplest sorting algorithms you get, and they're actually not that fast. They're not used anywhere because there are much faster sorting algorithms, but they're good for initial analysis. So we're looking at these algorithms so that we could learn how to analyze algorithms. I don't need you to memorize these algorithms. But it's good if you understand them when you're looking at them, or if you can follow the pseudocode and sort of see what's happening. Okay, so the next sorting algorithm we're going to look at and analyze is called the bubble sort. So we're going to look at both these algorithms first, and then we're going to analyze them. So this is the selection sort, and then we're going to look at bubble sort. It's very similar, but it's different in a few important ways. So what we're going to do is compare an adjacent pair of elements and swap them if they're out of order, right? And then we're going to sort of run down the list of unsorted items and compare them and swap them if they're out of order. This is actually a fairly straightforward algorithm. So if any swaps were performed, we reset the algorithm and start again. So if we've gone through this entire algorithm and we haven't performed any swaps, that must mean everything is in the proper order, everything's sorted, and we can finish. But if not, then we have to go through it again. So we're going to go through the list as many times as we need to until everything is sorted. All right, and we'll see this in action as well. So this is the algorithm, and this is our unsorted list, the same one as before. So what we're going to do is look at the first two adjacent items. So in this case, that's the 7 and the 3. And we can see that they're out of order. and we want to keep a flag. So we want to remember if we've made any swaps this pass, right? So this is essentially the algorithm. So we swap those two items, and then we move to the next two items, right? 7 and 9. We compare them. So we know we have a check mark here because we've made one swap this pass. So that means we're going to have to make it. We had at least one item out of place, so we're going to have to make another pass. But first, we're going to complete this pass. 7 and 9 are actually in order, so we don't swap them. Looks like we skipped a step. So the next two that we look at is 9 and 8. So for some reason, that slide happens to be missing. But those two happen to be out of order, so we are going to do a swap there. And then we look at the 9 and the 5. Those two are out of order, so we're going to swap them. We move to the next two, the 9 and the 2. They're out of order, so we swap them. 9 and 3, they're out of order. 9 and 1, they're out of order. All right, so that's one pass of the algorithm. And if we've set this flag, if we've done any swaps at all, then we're going to do another pass. And we keep doing that until we're not swapping anything out. All right. So can anybody see how this is sorting? Or maybe what's something you notice about the list now that we've made one pass? Is there anything we can say definitively about it? Yeah. So it's called bubble sort because the highest number is going to bubble its way up to the end. So the highest number happens to be in proper sorted order now. Yeah, so good. So then we reset the algorithm because we made some swaps, and then we do the comparisons again. So 3 and 7, they happen to be in order. 7 and 8 are in order. 8 and 5 are not, so we're going to do a swap. We check our flag because that means we're going to have to go through it again. That means not everything was sorted this time. 8 and 2 are out of order. 8 and 3 are out of order. Yeah, it's pretty similar to selection sort. It is. The main difference is, so 8 is going to bubble up to the top. And these two items are sorted. And in this iteration, we compare these two items, but as you're going to see, we don't have to. This is sort of a wasted. But yeah, so in selection sort, yes, for selection sort, the smallest goes to the beginning. That's correct. So in selection sort, we order it one item at a time, starting in the first, then going the second, the third. Bubble sort does something very similar, but it does the opposite. What if the numbers were not even? I'm not sure what you mean. So we don't, yeah, so we don't look at, so we first look at 3 and 7 on a pass, then we look at 7 and 5. So we don't, if they were even, we would have to look at these two, then these two, then these two, but that's not what we do, right? So we look at these two, and then we look at these two, and then we look at these two. So it doesn't matter if we have an even number of numbers or an odd number of numbers. We're going to compare each consecutive pair. Does that make sense? All right, good. All right, so we continue our bubble sort. So we compare 3 and 7, no swap, 7 and 5. And we know that's, just by looking at the list, that 7 is the next biggest item. So everything we compare 7 to is going to have to be swapped. And then 7 is, yeah, we've had some swaps, so we're going to do another pass. And now 7 is in the correct location. So 7, 8, and 9 are all in the correct locations. So let's just run through this. So next 5 is put in the proper place. Next, one of the 3s should go here. The other 3 should go there. And then, yeah, so that's our bubble sort. And this is our pseudocode for the bubble sort. So we set our flag here. That's the little checkbox we saw on the last page. And then we go from 1 to the length. So we go from 1 right to the end. And we see if the item at these two consecutive items are out of order. If they are, we swap them and set the flag to true. So we do that while that flag is true. And we ran it sort of inefficiently. So we go from 1 to the length every single time. However, we can make use of the fact that we know that every time we go through the entire algorithm, the next last item is in sorted order. So instead of going from 1 to the length each time, we can set this variable n and then decrement n every time so that we don't have to go to the end every time. All right, good. Any questions on bubble sort? All right, so here's sort of an animation of how these two things sort. So you'll notice the selection sort is, as we talked about, it starts at the beginning and sorts in that order, while the bubble sort starts at the end. Selection sort, less items are moved in general, whereas bubble sort things sort of flow down towards where they're supposed to be. Whereas selection sort is a little more, things aren't flowing, they're just moved when they're found. Bubble sort seems to have more swaps. Yeah. So we're gonna analyze that and see if that's in fact the case. All right. So the fundamental operation that we want to examine is visiting the individual elements. So we're going to look at how often selection sort accesses an element and how often the bubble sort accesses an element. Selection sort is to push elements up on the list, though. Those also kind of swaps. Yeah. Yeah, they do. So yeah, I mean, by all means, try and figure out which one does more swaps. So which one does more memory accesses. But we're going to actually count them. So where do we have fundamental operations, our memory accesses? Yeah. So this is the selection sort algorithm. So every time we access, so item represents our collection. Assigning the next smallest index. So when we're talking about these here, these are local variables. And these are actually, we don't really count those as memory accesses. 2 memory accesses per comparison and 2 for swap, actually 4 per swap. Yes, you are correct. So here's where our memory accesses happen. Every time we do a comparison, we access 2 places in memory. And every time we do a swap, well, so our swap is going to look something like this. So every time we do sort of these array index, so these square brackets, those sort of indicate where these memory accesses are happening. So we have our list, we access 1 piece of memory here, 2 pieces here, and then 1 more here. So that's 4 accesses per swap. So yeah, that's absolutely correct. Is that clear to everyone, how we're counting our memory accesses? All right. Yeah, so basically anytime you see, in a sense, these square brackets mean I've accessed a piece of memory. Especially, I mean, in particular, because this is a list. So if I do L, any number in here, that's a memory access. So we got 4 for our swap, and then here we can easily count 1 and 2. Those are other 2 memory accesses. So we have 2 there. Now we want to find out, so how many times each of those lines gets called. Okay, so here's our algorithm, and what we're going to do is we're going to count the number of times this loops, and we're going to count the number of times this loops, and we're going to use those to count all of these lines, how many times that line is executed, and how many times this line is executed. And we're going to assume, of course, that these things are in the worst possible order for us. So if it's a choice between maybe I didn't have to swap, we're going to assume that we did have to swap, all right? In this case, though, we always, well, technically, we always run this swap operation, even though we may not need to swap something. So our outer loop executes length minus 1 times. So that's this. Sorry, let's erase some of this. So that's this for loop here. And it's a static for loop. It's set up from the beginning with with these numbers. So it's not if you did a while true loop, then it's a little bit different. You have to maybe think about things a little more. But here we can see exactly how many times this loop executes. All right, so then we can use our sigma notation. So I equals 0 to n minus 2. So we're going to say the length, we're going to use n as the variable to store the length in our sigma notation. So to go from 0 to n minus 2 actually executes n minus 1 times, right? So this is what we want. Right? So is everybody sort of clear on that? The sigma notation is inclusive. So it starts at 0 and it ends at n minus 2 in this case. It's in a sense expressed differently from this line here, which is not inclusive. So because this does not include this value, we're actually going from 0 to length minus 2, so to speak. Okay. Is that clear? Any questions on that? A plus B minus 1. Where A is plus 1, yeah. Yeah, for the sigma notation, that's correct. So if A is the, yes, yeah, you're correct. Okay. Any other questions? If I've lost you, it's a good time to try and get caught up. So this is where the work happens. So now we do, let me clean this up a little bit. So now we do 4 accesses per swap. That's this line here. So this line executes every time this loop executes. So what we want to do is we want to put the 4, that's 4 accesses in that sigma notation. The inner loop, that's this one now, executes length minus I minus 1 times. All right, so the length, so if we figure out how many from I plus 1 inclusive to not this number, but not including that number, so this is actually from I plus 1 to length minus 1, that gives us this many loop executions of that loop. Okay, so these are really, they're a bit of a pain to work with, these different sort of parameters where one is inclusive and one isn't. You'll get used to it. We use this notation here because this is actually Python, how Python executes, and it's actually how most computer languages execute, is they include the first term, but they don't include the last term. But then when we do the math actually includes, if we write a loop in math, it includes the first term and the last term. All right, so this loop executes length minus I minus 1 time, and how we express that in sigma notation is right here. All right, so this actually executes n minus 1 minus I plus 1, and then we add 1 because it includes the first item. So if we, so if we cancel off this, cancel this one and this one, we get, no, sorry. It's n minus 1 minus I plus 1. So it's actually n minus, and then we add 1 for the, to include this item. So yeah, as you can see, it gets a little confusing. So it's n minus 2 minus I plus 1. So it's n minus I minus 1. Okay. So yeah, those are, again, this is going to be a rather difficult example. And then for each of these passes, we get 2 axes. So that's every time we execute this loop, we do this comparison. So we have 2 axes. All right. Yeah, we kind of jumped ahead there. So then let's look at, so this is actually expresses all the memory accesses that we do. So this is how we're going to analyze this algorithm. And these are operating on constants. So we want to first do this one. So again, this executes n minus 1 minus I plus 1 times, and all of that is times 2, right? So that's going to be 2 n minus I minus 1 times. So I can write this sigma notation here as this. Okay, so that's going back to when we did sigma notation. Any questions? This might be getting a little confusing. So here we've expressed this sigma notation as this. Okay, so then let's break it down a little bit further. So now all of this is included in this sigma notation. So what we're going to do is we're going to split over addition. So that's, if you recall back to when we did the sequences, sums, and series. So we can break it down into 2 separate sigma notations by dividing over this plus sign. Then this guy is a sigma notation running on a constant, so we can evaluate it to 4 times n minus 1, since it executes n minus 1 times. And then we have to evaluate this guy. So we're going to break it down. So we distribute this 2 over the n minus 1 and over the I. So we're going to break it down into these 2 things because here the n is a constant, and here this I is part of this sigma notation. So we have to evaluate them differently. Okay, so then we can split over this addition or subtraction in this case. So now this n is a constant. This executes n minus 1 times. So we're just going to multiply the 2 n minus 1 that we find here by n minus 1. And then we can move the constant 2 out front of this sigma notation. And this is, of course, if we do I equals 0 to n minus 2, that's equal to n minus 2. Well, that's basically the one that you should memorize. If I have I equals 1 to n, then it's n plus 1 over 2. But since I'm doing it from 0 to n minus 2, then I end up with this expression. Okay, so then you can, I'm not going to right now work through all of the algebra, but if you multiplied all those things out and then combined them, you would get this expression. So this is the number of memory accesses as a function of the input size. So that's the length of the unsorted list. Okay. And so maybe, hopefully this didn't confuse you too much, these steps, but these are all very straightforward ways that we evaluate summations and series that we took a couple weeks ago. So hopefully you can follow them. If not, it's all in the notes, or you can ask questions. But yeah, any questions? Okay. So that's selection sort is, we've analyzed the number of, we picked our model of computation, we've analyzed a number of memory accesses using our sigma notation. Now we're going to do bubble sort. So here we can see the swap does 4 accesses, and this comparison does 2 accesses. And really, all of those occur inside this do while loop and also this for loop. So now when we analyze the for loop, it's very straightforward. It's from 1 to n, and then we decrement n each time. The maximum number of do while loops is a little less clear because we're going to exit as soon as we hit this flag. But we're going to assume in the worst case that that the flag, that we do a swap every single time until the worst case, basically. So in the worst case, we can loop through n times, because each time we loop, we've set 1 more item in place. And since there's n items, it'd take at most n loops. It actually would take at most n minus 1 loops, because once you have n minus 1 items in position, then the last item has to be in position as well. And this is, so the maximum number of inner loops on the first pass is n minus 1. Maximum number of inner loops on the second pass is n minus 2. So this is actually executes n minus 1 times here. But then we decrement the n every time we do a loop. Okay, so let's, given those parameters, let's analyze this. So the outer loop executes length times, where length is equal to n. Inner loop executes length minus 1 times, so that's n minus I. And then 2 accesses per comparison and 4 accesses per swap. So we get this. And if we, so again, this is just j equals 1 to n minus I of 6. So this actually executes n minus I minus 1 plus 1 times. So we get n minus I times 6, which is where we get this now. So now we just have this last summation to evaluate. All right, so we're going to take the constant out, and then we're going to break it down over addition, because these have to be sort of evaluated separately. So here we're going to do evaluate the n, and here we're going to evaluate the I. So the n is simply, this loop executes n times, so it becomes n plus itself n times, so n squared. And then this is actually, of course, our n times n plus 1 over 2. So if we evaluate all that out, do some algebra, which I'm not going to bore you too much with. The algebra should be very straightforward. So we get 3n squared minus 3n for bubble sort. Okay. All right. So any questions? The left side, why isn't the left side n times n plus 1 over 2 as well? So let's go back then. So the difference is, so you're talking about this step, I presume. So in this case, because we have I here, but we have n here. So n is actually, yeah, it can be a little bit deceiving because n appears here, so we naturally think it's a variable and it takes on different values, but it doesn't. It actually, this stays the same value. N is a constant. So this loop here, I equals 1 to n of n is equal to n plus n plus n plus n, n times. So that's equal to n times n, or n squared. Okay, whereas this here is equal to 1 plus 2 plus 3 plus up to n. So that's why we get this n plus 1 over 2. Yes, there's only one n here, and it's the length of the list in this case, and which is a little bit confusing because we've used it in the algorithm. We used it as a variable where we decremented it every time. So in this case, though, the n represents the length of the list. Yeah, I should change that. That's not. That's a little bit confusing. But yeah, here it represents the length of the list. And so then at this point, although it's a pain and it's tedious, this part should be straightforward. It's just algebra. All right, so these are the two sorting algorithms. So we've gone through the pseudocode, or we've gone through the algorithm. We've, in a sense, made pseudocode. We've counted the number of significant operations, in this case, memory accesses. So now we have sort of a running time of these two algorithms. So if you plot them out, you can see that the bubble sort is actually slower in terms of memory accesses than selection sort, in the worst case. So assuming we have completely unsorted lists where every time we pass through, we have to do a swap, and we always have to pass through the maximum number of times. Okay, so now, what do the x and y axis represent? Yeah, so this is the number of memory accesses. And this is the problem size. So, or if you will, the length of the unsorted list. So yeah, I guess I should label those axes. Okay, so we can see basically, we're seeing how these two, how the runtime grows as the problem size grows. So we can see sort of that bubble sort grows faster than selection sort, but is it significantly faster? That's sort of what we're going to be looking at next. Okay. Any other questions? All right. So we have these two, I guess, expressions. So at very large values of n, the higher order terms dominate, right? So n squared for a large value of n is way, way bigger than n log n, which is in turn way bigger than n, which is in turn way bigger than log n. So when we're looking at these, we're going to focus on the sort of the biggest term in terms of the polynomial size. So we're going to sort of ignore the lower order terms. And then we're going to also ignore the constants. So because in terms of how big n can get, if we're talking about large problem sizes, if you're working somewhere and you say, well, I made my algorithm 3 times as fast, they're going to be pretty impressed. But generally speaking, that's not as important as managing this polynomial here. This n squared is more important than whatever constant comes out in front. All right, so whatever number is here is more important than whatever number is here in terms of how fast this function grows. So we're going to sort of ignore those constants as well. So now we get that both of these are sort of approximately equal to n squared. And then, so this sort of rounding off of these functions and approximating them, looking at the highest order term and ignoring all the rest, are the foundation of something called big O notation. And big O notation is something we use to analyze algorithms in computer science. It sort of tells us, it gives us, it doesn't give us all the information, but in a sense gives us the most important information. Although, like I said, if you went to your boss and said, I made this algorithm 3 times faster, they would be impressed. Okay. Any questions on that part? Okay. So now we're going to look at, so that's how we analyze basically straightforward iterative algorithms, where we use for loops, we use while loops. So we can change those for loops and while loops into the sigma notation, and then we know how to evaluate that sigma notation. That part's pretty straightforward, even though it looks like a big mess and complicated. The rules are actually very straightforward, and just apply them until you get to some closed form expression. But now we're going to look at a different type of algorithm and a different type of analysis on that algorithm. So again, this is back to the searching algorithm that we looked at earlier. So let's say we're looking through a telephone directory back when there was such thing as a phone book. You start at the first page and check every single name and sequence until you find the one you're looking for. So that's sort of the naive approach. This is the linear search that we looked at earlier. And here, well, this is the binary search that we looked at earlier, where we use the fact that everything's in sorted order to jump around to find something quicker. So we're going to describe each approach in pseudocode and then express the time complexity of each one. So linear search is quite easy. Every time we have one loop and we have one memory access, and so everything is very straightforward. Goes from the loop executes the length of the list, and each time we have one memory access. So this is going to be n memory accesses. So to run linear search, if we express it in terms of the problem size, it's simply n. All right. So here, yeah, if we're searching for R8, we would start at R1. It's not there. Look at R2. It's not there. Look at R3, et cetera, et cetera. So by the time we find the one we're looking for, we've looked at everything from the start up to that item. And then binary search, here's the pseudocode for binary search. So we saw it expressed in English earlier. And this is how we would express it using pseudocode. So you'll notice that this is a recursive algorithm. And what does that mean? That means from within this method, I call the method again. So within the method, the method calls itself, right? But it calls itself with a reduced problem size. So if we look at, we send in a list, we send in the key that we're looking for, we send in a low index and a high index. If we get to a list of size of 1, then the high index is going to be less than the low index. I'm not going to get into the details of why. Yeah, what if the list in binary is an odd size? Well, that's fine. Generally speaking, when you split it up, what happens here is this is actually a floor function in most programming languages, right? So this is going to round down, and then so you're going to always sort of look at if I have an even number of items, if I have 1, 2, 3, 4, 5, 6, then my center is going to be 3, right? So the center would be here, but it's going to round down. So yeah, it's going to be a little bit offset if you have an odd number of items. You'll have, and then when you recurse, you'll have 3 in this sublist and 2 over here, but it's going to roughly be half. It'll be at most half. So yeah. So each time we go through, we compute the center, and then we compare the center to the key. And then depending on whether if the thing we're looking for is less than the thing we're looking at, our center equals low plus high minus low over 2. I would have to see the rest of the code to be able to answer that. Off the top of my head, why would you do that? Right. Is it mathematically the same? High minus low over 2? Oh, yeah. Oh, sorry, yes, minus. Okay. Yes, it's mathematically the same. Yeah, so low plus high minus low over 2. Right, yeah, that makes sense. No, so this is actually functionally the same as, it gives you the same answer as this, essentially. Maybe it might be plus or minus 1, but it's essentially the same thing. It's just, yeah, because you're using the minus instead. So you're saying, what's the difference between low and high? Yeah, it's the same. Okay. So now we want to rate. Good. Any other questions or observations? All right. So essentially, the important things to note here is every time we haven't found the item that we're looking for, we cut our problem size in half and we make a recursive call. And then at the end of it, we return the center. And we're going to assume that the worst case that we have to go through until we find a list of size 1, and then either the thing exists there or it doesn't. So we're going to assume that that's what happens in the worst case. All right, and then this is sort of the, we saw this earlier, but if we're searching for R8, we start looking at the middle. R8 is greater, so we're going to look in the right-hand half, and then we look at the middle again. R8 is less, so we're going to look at the left-hand half. R7, R8 is greater, and so finally we settle. The fourth thing we look at is actually the thing we're looking for, using this binary search method. So linear search, the best case scenario is, of course, well, it's the first thing we look at, let's say. What's the worst case scenario on linear search? Well, we talked about that, right? But if it was at the end, then we have to search through every single page, every single record, until we find the thing we're looking for. Average case would be about n over 2, right? If all other things being equal, if we randomly pick a name to look for each time, the average case, we would search half the items. On a binary search, of course, now we're going to start at the middle, but maybe we find it on our first try. But what's the worst case now? And I guess what's more importantly is how do we calculate the worst case? So, so when we do a recursive algorithm, our process is a little bit different. So we're going to say, let T of n be the number of accesses to search the array of length n. Now we don't know the exact value yet, but we're going to sort of try and express it in a way that it lets us get there. So on every call to binary search, we do 1 access. So actually here we're doing 2, but a wiser thing would be, say, to store, list, center, and then that only takes 1 memory access per call to binary search. All right, so we don't do it here. And the other thing is that, well, 1 or 2 they're both constants, they're both small constants, so it's not really worth differentiating them. So yeah, we're gonna call it 1. So 1 memory access every call to binary search, but then we're gonna do a recursive call on a problem of half the size. Okay, so does that make sense to everyone? So this is the total number of accesses, 1 plus however many I have to do here, and that's the total number of accesses. So now, how many do I have to do here? Well, we have an expression for that, right? So here, instead of n, we can say, well, substitute n over 2 for n, and then we can express t of n over 2 as 1 plus a recursive call on half the problem size again. All right. So we can substitute back this expression for this, the t n over 2, and we can substitute this in for that. All right. So is everybody clear on what we did there? So now we can simplify that. We take the brackets away. We can add these two things together. We get 2 here plus t of n over 4. So now we have a new expression that is equal to this expression. But you'll note that we can actually express t of n over 4 as 1 plus a recursive call on something that's half the size. So again, we could substitute that in, and now we get this 3 plus t of n over 8. All right, and then we can carry on that same pattern. So this is, when we substitute back, this is called unfolding. There's some other names for it too, but this is the one that I'm most familiar with. I forget off the top of my head what the other names are. But we call this unfolding because you're sort of, you keep substituting back into the original recurrence until you start to see the pattern. And so the pattern is this increments by 1, and the problem size gets cut in half every time. And all of these expressions are equal. Okay, good. So question is, what is this ultimately equal to? Well, if we keep following this pattern, we get, of course, k times here. So we're going to assume that this executes k times. So we have k recursive calls to binary search. So then my final expression looks like this. Okay. So now we want to find out what is k equal to. So how many times does this execute? Well, it executes until we're down to a list of the size of 1, and then we can't recurse anymore. So when we reach t of 1, so when t of n over 2 to the k is equal to t of 1. So that means we want to find a k such that n over 2 to the k is equal to 1. And so if we do a little bit of algebra, we move this, we multiply both sides by 2 to the power k. We get n is equal to 2k. We take the log of both sides, log base 2, so we have log of n is equal to k. So basically, we know that k is equal to log n because we know we're going to stop when we reach a list size of 1. Right, so then, yeah, so now this is equal to 1 by substituting this log n in for k. All right, so this is, we'll go over this in a bit, but 2 to the log base 2 of n is equal to n, basically. So the final expression is t of n is equal to log of n plus, so since k is equal to log of n, we get log of n plus t of 1. And t of 1, there's no comparisons. We just check if high is less than low. So there's no memory accesses there. Can you just ignore the log base of 2? In the analysis, yes. It's important in terms of it's sometimes you can, right? Sometimes you should not until you're finished. When you're done, it doesn't matter. But while you're doing your computations, so here the log base 2 is sort of important because we know it's log base 2 because we cut our problem size in half each time. Yeah, is a t 1 equal to 1? Not that it matters. Exactly. But if we look back at the algorithm on the final one, and I didn't go really into detail as to why that is, but if high is less than low, it returns. So there's no actually memory access in that final one, and this happens on a length of 1. But you're correct in that. So if I could actually add +1 here, and that doesn't really make a difference in terms of what we're interested in analyzing, which is this log of n, which represents the growth of the function. So +1, -1, it's not that important. Okay, so how much better is binary search than linear search? Let's assume that the array that we're searching is doubled in size. So how much worse is linear search? Well, linear, if I double the size, it takes 2n memory accesses instead of n memory accesses. Binary search, if I double the size, log base 2 of n and log base 2 of 2n, well, log base 2 of 2n is equal to log base 2 of 2 plus log base 2 of n, and log base 2 of 2 is equal to 1. So in binary search, if I double the size of my array to be searched, I'm only adding 1 extra memory access. So it's very, very efficient. And you can see here, so graphed, this is the problem size, this is the time required. So linear is, of course, a straight line along the diagonal. So that's this O of n. And then the O of log n grows way, way slower. And then, of course, constant is simply a straight line along the x-axis. Okay. All right. Any questions? So that's how we analyze a recurrence, recursive algorithm. It's called a recurrence relation or a recurrence expression. Yeah, we use that unfolding technique to spot the pattern, and then once you spot the pattern and you know what your base case is, you can determine how many times you've executed. You've made that recursive call, and then you can figure out how many memory accesses or whatever it is you're analyzing there are. All right, so some of the things we looked at mathematically. So an exponent, so if I have b raised to the power x, that's equal to b times b times b x times. And we can also express it like this. So in addition to sigma notation, this is, oh geez, off the top of my head, I don't know. It's another Greek letter, but this represents multiplication. So if I had 3 to the power 5, I could express that as 3 times 3 times 3 times 3, or I could express it using this. Is that, I don't know what that is. Is it pi, capital pi? All right, so it's pi. Logs, so log is sort of the opposite of the exponent, but it's the value that satisfies the equation. The value x that satisfies b to the power x is equal to k. So if we substitute log base b of k, so if we take the log of a number and then we take the exponent to the same base, we get back the number. So the exponent and the logarithm are sort of opposites, inverse operations, and it's approximately the number of times b divides k before we get a value less than or equal to 1. Right, so for example, I take a log base 10 of 6 and I raise it, I raise 10 to that power, I just get back the number 6. Log base 10 of 1,000 is what then? So how many times can you divide 1,000 by 10 before we get down to 1? That's very straightforward, yeah, 3. So then log base 10 of 1,000,000, this would actually be 6, right? So that's pretty, a logarithmic function is actually pretty efficient. Even log base 2 of 1,000,000 is something like, is about 20. So even if I'm processing 1,000,000 things using that binary search, it's not going to take me very long to do it. Log base 3 of 9 is what? 2, yeah. So the number of times we can divide 9 by 3 is 2. Log base 2 of 32, does anybody know this one? So in computer science, we see log base 2 a lot. So you'll get used to these numbers after a while. 5, yeah. Good. So another thing, if we want to change the base of a logarithm, well, what's the difference? So if I did log base 2 or something, or log base 10 of something, is there a big difference between those two things? Well, so what do we want to put here for the constant, or what do we want to put here for the expression? What expression should take place of that question mark? So actually, if we want to change the base, if we want to change from a base of b to a base of a, we're going to divide by the log of a, base a, the log of b, log of base a logarithm of b, basically. Right. So what that means is that log of base a of b is a small constant. So we've seen how slowly the logarithm grows. So even if these are vastly different, it's going to end up to be a small constant. So logarithms in a different base differ only by a constant. N factorial, so all the positive integers that are less than or equal to n. So it's n times n minus 1 times n minus 2 times et cetera, down to 1. And we can express it using this pi notation. For instance, 5 factorial is 5 times 4 times 3 times 2 times 1, which is 120. And here's all basically a lot of the very common sort of run times of algorithms that you'll see. Well, hopefully you don't see these guys. And here they are sort of relative to each other. So n factorial, oops, and 2 to the n are very fast growing functions. N squared is pretty fast, and n log n, yeah. So this is called, O of 1 is called constant. This is called logarithmic. This is linear, quasi-linear. This is polynomial. This could be, this doesn't have to be a 2. It could be a 3, 4, any number. Exponential is if I raise some constant to the power of the problem size, and n factorial is, of course, n factorial. Okay. So any questions on any of that? Exponential factorial algorithms even exist, never seen one. They do exist. The thing is they run so slowly that they don't really get used. You will see them. If you do, well, one of the popular ones is if you do calculate a Fibonacci number using a brute force algorithm, that's actually an exponential algorithm. So, you know, every time you add 1 to the problem size, if you calculate the nth Fibonacci number, then the n plus 1th Fibonacci number, it's going to take twice as long roughly speaking. What algorithms are O of 1? Well, I mean anything. So an array, if I access an array and I know the index, that's O of 1, right? That's just one memory access. So if I want to look at, if I only want to look at one location in my array, that's O of 1. Yeah, so those are common, but they're generally part of some bigger, of course, algorithm. Polynomial is fairly common, but even you know, once you get past n squared, even like n cubed, that's rough. It slows down really quickly after a while. N log n, this is all your search algorithms are going to be n log n. This is very common, or not search, sorry, sort. All your sort algorithms are n log n, so that's a very common one, and that's sort of the best you can do for sorting, for comparison-based sorting. So you'll see plenty of that as you advance in your degree. Any other questions? Okay, so let's take a 10-minute break. I have 7:01, so let's come back at, well, we'll say 7:12. And then we will go into big O notation. All right. All right, so we're back. I'll take questions in a minute. I just want to show you one thing. So this is the specification for assignment 4. Possibly it'll look something like this. So I just wanted to show you what you're sort of expected to take away from that, the first half of the lecture. So you'd be analyzing something like this. So it's just some gibberish algorithm, and you're going to count the number of times you execute foo and count the number of times you execute bar, given that we have these for loops set up. All right. So this is not, so this is assignment 4. This question will be very similar to this, although I'm going to take a look at it and possibly change a few minor details. But yeah, so just so you understand what you're expected to have taken away from that last lesson, which I feel like had a lot of details, you should be able to analyze this, basically. So that means express it in sigma notation, and then I give you some problem size. Here's 2000, and you compute how many times each of these significant operations executes. Okay. All right. So any questions on any of the things that we saw? Okay. Good. So let's move on then to big O notation. So it looks like we might actually get through everything we were supposed to tonight, which is an interesting development. Okay. So that's sort of, so we looked at how we analyze algorithms, and this sort of builds on top of that. Now, when we express an analysis, instead of saying, you know, we could say that, well, you know, n squared is the most significant term, 3n squared or whatever, so it's approximately n squared. We saw that. But we have a more formal way of expressing it, and that's using this big O, big theta, big omega, and big theta notations. Now, again, these are based on the slides of Dr. Robert Collier, and I've modified them, so any mistakes you see are likely mine. So before we look at this big O, big theta, big omega notation, we're going to take a quick introduction to functions. So these are ways of analyzing the growth of functions, and in particular, they're functions that express, you know, how quickly your algorithm runs, but they are functions, and functions do have some specific definition. So the rate of growth of an algorithm is expressed as a function of the problem size. So what is this function thing? So we're going to look at it in more detail a couple lessons maybe next week. But for now, we're going to give you enough of an introduction so that hopefully you can start understanding what they are. There, yeah. So mathematically, a function is analogous to a method or a subroutine in programming. If you're using Python, actually, we call them functions as well. So what does that mean is a function has some input. So in a program, there would be the arguments, the stored in parameter values. And we have some output, which is the return value. And as we talked about with computers, computers always do exactly what they tell you to. So when I say input, for a given input, a function always returns the same output, all right? And you can even think of it, even if you have random numbers inside your method or function, you can think of it as, well, the random number becomes part of your input. So if I give you some specific input, you are going to give me one and only one output. So that's sort of the definition of a function. So more generally, a function is a mapping from a set of inputs to a set of outputs. But there's something, so here's an example of a function that's a computer program, a computer method. Then we're going to use that to sort of illustrate what a function is. So a Gregorian calendar, a normal year is 365 days, but a leap year, any year that is not divisible by, or any year that is divisible by 4 is a leap year, and it has 366 days, except a year that is evenly divisible by 100 is a leap year only if it is also divisible by 400. So this is a little bit convoluted, but this is very straightforward for a program to compute. So if we had a function, is this a leap year? We have the input parameter is the year, and the output parameter is going to be true or false. All right, so here's all the things that we just described. Here's how we would express them in pseudocode, and if we program this up, we can make this function, is this a leap year? So now, if we want to write this as a mathematical function, though, we're going to, express it a little bit differently. So we have our set of inputs. So this is a set of all possible years, right? Set of all years, and that's even, you can even think of it as an infinite. So it's not unusual to have infinite sets in math. And then for each of these, we map it either to true or to false. So we take all these numbers and we draw a line from set A to set B, saying that, well, if I get an input of 1583, given the algorithm that I just saw, I'm going to get a return value of false. So that's what a function means, is that a function from set A to set B is an assignment of exactly one element from set B to each element of set A. So each of these, if I give it as input, will generate an answer, and it will only generate one answer. So I can't have something like this, right? That's not a function. So if I give you this year and it's sometimes you return true and sometimes you return false, that's not a function. So when we talk about functions, that's what we mean. We have each item on the input maps to exactly one output. And we can write it like this. So a function of A equals B is indicates that B is what is mapped to that unique element A, where A is a member of some set, some input set A. Okay, so we talked about each item of the input gets exactly one output, and how you can do that is if you sort of plot it. So if you have the input as a map of numbers and your output as a map of numbers, although it doesn't have to be, but a function is something that if I drew any vertical line, I'm only going to intersect it once, right? So if this instead went up and then curved back like this, I just made a dollar sign, but that's not a function because at this given point, this is the input here. I get more than one possible output. So I have an output here, a possible output here, a possible output here. So that's not a function. When we're talking about functions, this vertical line test is one way that we can verify that it is indeed a function. All right, so now when we're talking about big O, we want to be able to express function behavior. So specifically, we want to look at the rate of growth of a function. And what the expressions that we saw in our time complexity analysis are functions. So given some input size of n, I'm going to generate some unique output. So it's going to take me a certain number of memory accesses in order to do whatever it is I'm supposed to do. This is also referred to as the order of the function. And the growth of a function is determined by the highest order term, since it grows the most quickly as the argument gets larger. All right, so and if a problem size is small, nearly any correct algorithm will be fast enough. So for instance, 2 to the n is a very fast growing function. But if we have a problem size of 3, then we need 8 memory accesses. That's going to run very quickly on just about any kind of computer. But if we have a time complexity of n to the 4 and a problem size of 10, then we need 10,000 memory accesses. If we have a problem size of 100, then we need 100 million memory accesses. And if we have a problem size of 1,000, we need, what is this, 1 trillion memory accesses. And none of these input sizes are particularly large. So the highest order term is going to dominate the growth of the function. Right? Yeah, so time complexity becomes important on large problem sizes. These companies here are all very interested in the time complexity of your algorithm. And in particular, they want to make these polynomials as small as possible. So for a very large problem size, n to the x is way greater than n to the power y, if and only if x is greater than y. And here's just more flavor of what this means, this time complexity. So if we have a function, our time complexity is expressed as 5n cubed plus 5. Then for n equal to 100, let's say we improve this program to 5n cubed plus 4. So what have we accomplished? Well, we've done one less memory access. But what if we improve the constant here? So what if we improve this 5 to a 4? Well, then we've gone from 5,000,005 to 4,000,005, which is a little bit better. But what if we reduce the size of this polynomial? Well, then we've gone from 5,000,005 to 50,005. So it's an order of magnitude faster. And yeah, so coefficients and constants are not nearly as important as the highest order terms. The behavior of the algorithm is more important than the speed at which an implementation runs. And when we talk about the behavior of an algorithm, we're looking at the shape of the time complexity function curve. So you've seen a bunch of graphs at this point. So here's a few more. So this is a function of x squared. And then if we have 2x squared, we have this orange curve, which grows, as you can see, faster. We increase the constant again to 5x squared. Again, we get a faster growing function. And now if we have this x cubed, so again, this is the, I didn't label my axes, but this is problem size. And this is time complexity. You can see that O of x plus y possible. Can a function take two different inputs? Yeah. So if we're not talking about, sorry, I thought you meant X and Y axis. No, but yes, a function, sure, it can be two different inputs. Although I'll be honest, I haven't seen that often in practice. But yeah, you would analyze, you would probably write it as O of X. Have I seen that before? I may have seen that before. You'd probably write it something like that instead of O of X plus Y. You would express it in terms of one of the inputs and the other. So yeah, it's possible. All right. Any other questions? Okay. So here you can see again. These are very small problem sizes. This is up to 4. Small problem size. And you can see this x cubed. At first, it's being dominated by the larger constants. So it passes the orange one here, but it still hasn't passed the green one. But if we extend our timeline a little bit, then you can see the x cubed really dominates all of these other functions just based on the size of this exponent, the polynomial size. Okay, so that's just sort of flavor of what we're looking at. So now we're going to get into the specifics of Big O. Before we do, any questions? All right. So let f and g be functions from the set of integers to the set of real numbers, or the set of real numbers to the set of real numbers. So we say that, so these are both functions, and we say that f of x is big O of g of x. So this is pronounced big O. If there exists constants c and k, with c, both of them are positive numbers, such that for all x greater than k, f of x is less than c times g of x, less than or equal to c times g of x. So this is sort of the mathematical way that we express big O notation. We'll go into some examples and some details. So f of x is said to be big O of g of x. And so technically when we use big O notation, this is actually a set of functions. So it's the correct way to express it is using this set notation. In practice, we often do stuff like this. So this is fine. Although it's technically not correct, everybody uses it. It's become sort of a common practice. This thing is technically the way you should be writing it, since this is the big O notation is a set of functions, but yeah. So the constants c and k are said to be witnesses. So we're going to do a bunch of examples to make sure that hopefully you guys get the hang of everything that we just said there. So stating that f of x is big O of g of x is equivalent to stating that after a certain size, f of x is always less than some constant multiple of g of x. So g of x sort of bounds the growth of the function f of x. G of x can be considered an upper bound of g of x. Right? And this big O notation is used to express the presence of an upper bound on time complexity. So if I say something is big O of x squared, that means that you can assume that it's at most going to be some constant times x squared in terms of runtime, where x is, so here x is just some generic input, but if we were expressing an algorithm, then x would be the input size, right? But we're talking generally, so big O is a way to bound functions. but we use it to bound algorithms, because algorithms, the output could be expressed as a function, the runtime. So for instance, if I have this function here, x squared plus 200, I could say, well, when x is greater than or equal to 15, x squared plus 200 is less than or equal to 2x squared. So therefore, I could say that x squared plus 200 is big O of x squared for k equal to 15 and c equal to 2. So the k equal to 15 is somewhere here. So actually, x squared plus 200 becomes bigger than 2x squared at 14 point something, but definitely at 15. And then for the constant 2. All right, so then this orange becomes an upper bound on the blue once I pass this line. Okay. Questions on that? Again, we're going to see plenty of examples, so but if you do have questions, please let me know. So how would we show that there's an upper bound of x squared on an algorithm with a worst case time complexity function of 3x squared minus 20x plus 100? So let's say we wrote an algorithm, and we analyzed it, we got this function is the time complexity. Time complexity. We could plot it out as we just did. Plots are not proof, but they're very helpful. Or we can instead observe that when x is greater than 0, this function is less than, so 3x squared minus 20x plus 100 is less than or equal to 3x squared plus 100, right? Because we've just dropped a negative term, okay? And when x is greater than or equal to 10, well, 3x squared plus 100 is less than or equal to 3x squared plus x squared. So in this case, x squared is 10 squared, which is equal to 100. So we can make those two simple observations. And then, well, if we add this 3x squared plus this x squared, we get 4x squared. So if we write this whole thing out, we have f of x is equal to 3x squared minus 20x plus 100 is less than or equal to 3x squared plus 100, less than or equal to 4x squared when x is greater than or equal to 10. So in other words, that's sort of what I just wrote. So f of x is big O of x squared because there exists some constant such that when x is larger than that constant or equal to that constant, then f of x is bounded by 4x squared, right? So c equals to 4 and k is equal to 10. Those are the witnesses that we use to bound this function. Questions? All right. Okay, I'm going to switch now to OneNote, and because we're going to get into some examples, and it was easier to express on OneNote than on the slides. Yes. Yeah, that's basically why we picked 10. You could have picked something even higher than that, right? But 10 worked, so we picked 10. Okay, so this is what we just looked at. So this is what I'm going to, so if you look in the notes, you have I did the PDF version of the slides, but I'm also going to do this. So I found out you could print the slides directly onto OneNote and then add your examples in. So I'm going to, after this lecture, I'm going to print this off for you guys, and then that can be part of your notes with the examples. Okay, so let's Let's do some examples. So before we get to so this is where we left off. So now we're going to prove that, how can we prove that 5x squared plus 10x plus 3 is big O of x squared? Well, it's big O of x squared if and only if, so f of x is O of x squared if and only if there exists c and k such that for all n greater than or equal to, or let's stick with x, sorry, x greater than or equal to k, f of x is less than or equal to c times x squared. Okay, so this is the definition of big O. So if we can find c and k such that this is true, then we've proven that our function is big O of x squared. Okay, so then, so I'm going to show you the first example. I'm going to show you a little more formally, and then I'm going to show you what we expect of you on an assignment or a test, which is going to be less formal. Actually, the quizzes will be multiple choice. So, but on an assignment, you can get away with without doing all the formalities here. Okay, so then, so we want 5x squared plus 10x plus 3 is less than or equal to 5x squared plus 10x squared plus 3x squared for all x greater than or equal to 1. Right, so this is, if x is greater than or equal to 1, then this holds true. Right? So then 5x squared plus 10x plus 3 is less than or equal to 18x squared when x is greater than or equal to 1. So then, let me see here. So if we wanted to do this formally, then we would say there exists a c such that for all x greater than or equal to 1, 5x squared plus 10x plus 3 is less than or equal to cx squared, and that is existential generalization. And this, of course, these two steps would be math. And then we would say, since we have a 1 here, we could say there exists c and a k such that for all x greater than or equal to k, 5x squared plus 10x plus 3 is less than or equal to cx squared. Again, that's existential generalization. And then, since this is one of the facts that we're given, or we can use it freely because it is the definition. So we have this double implication. So I could sort of skip a step and say that, well, this implies that 5x squared plus 10x plus 3 is O of x squared. And just that's the definition of big O. Okay. So that's formally how we would show that this function is big O of that. So first we would find the values for C and K specifically, and then yeah. So C is equal to 18 and K is equal to 1. For these values, we've seen that this is big O. Because these values exist, this is big O of x squared. In practice, we would not do this existential generalization simply because the patterns are so easy. All you have to do really is find this C and K. So yeah, so let's, if I started over, I would say 5x squared plus 10x plus 3 is less than or equal to 5x squared plus 10x squared plus 3x squared, which is less than or equal to 18x squared. Therefore, 5x squared plus 10x plus 3 is big O of x squared with C equal 18 and K equal to 1. And you can write as witnesses. But yeah, and you should specify here in this step for all x greater than or equal to 1. Okay, so this is actually all that we really expect of you. If you're going to prove something is big O, you don't have to do all this formal stuff. But this is sort of what's happening behind the scenes, is all this formal. It's still a formal proof, but because they all follow the same pattern, we can skip all those steps. Just mathematically show that this C and this K exist, and then that's enough to prove that this is big O of x squared. Okay. Any questions? All right. So is 5x squared plus 10x plus 3 big O of x cubed? So is this true? Anybody want to take a guess? So technically, yes. So we have a no and we have a yes. Technically, the answer is yes. So this is true. And you can prove it by saying, well, 5x squared plus 10x plus 3 is less than or equal to 5x squared plus 10x squared plus 3x squared for all x greater than or equal to 1. And then that's less than or equal to 18x squared. And that's less than or equal to 18x cubed when x is greater than or equal to 1. Right? So technically, we found a C and a K such that C is equal to 18, K is equal to 1 as witnesses. Right? So technically, I should say 5x squared plus 10x plus 3 is equal to O of x cubed. So that's true, but this is not, this is not as useful as it could be. Generally, we want stuff, we want to find the bound as tight as possible. Yes, it would hold for all of x to the power n for n greater than or equal to 2. It's also true that I'm not going to get into this specific example, but this is also big O of 2 to the n or 2 to the x. It's also big O of x factorial. So any function that grows faster than this function technically this function is big O of that, of any function that grows faster. But we want to try and find bounds as tight as we possibly can. It's just more useful. If I say it's big O of x cubed, well, I'm not really, okay, it grows at most x cubed, but if it's only a linear function, well then I've sort of deceived you a little bit, right? I haven't really said anything that's false, but I haven't really given you any useful information. All right. What else? Yes. So here's the slide that we left off at. So let's express this more generally. So any sort of polynomial function can be expressed as in this form, right? And these are so an minus 1, etc. are constants. Could be negative, could be 0, could be positive as well. So basically any polynomial function we could express this way. All right. So now, how do we prove that this is big O of x to the? So how do we prove that this is sort of the dominant term? I'll first define the correct page. So we can use limits at infinity. Yeah. You guys want to learn limits? I could show you limits. I like limits. We don't use them in this class. So just to keep things, just to keep all your answers consistent, and so that they're easier to mark, we basically stick with this definition. We basically stick with this definition of using the C and the K as witnesses, but there is a way that you can prove this using limits of functions as x approaches infinity. And maybe I'll show you that, but that's not, just to be clear, I expect this definition, the C and K as witnesses. This is the official definition of big O that we're using. But I'll show you, next class I'll show you how to use limits. Okay, so then how would we show that? So now we want to take this function and show that it is a big O of x to the power n. So what we do is we express it. So we take the, first of all, absolute value of the constants, the n plus a to the n minus 1, x to the n minus 1 plus, etc. A1 times x plus A0. And then we observe that that's less than or equal to an plus an minus 1, the absolute value again, an minus 2, etc. And then multiply all that times x to the n, right? So what sort of the steps that we skipped is we, each of these terms we increased to the maximum polynomial, and that's for x greater than or equal to 1. So then what we've shown basically is that if we take c equal to this constant plus and k equal to 1, then those are sufficient witnesses for any function, any polynomial function. Because this is going to be, sorry, this should be less than or equal to here, right? So if I changed any negative constants to positives, then this function here is going to be less than or equal to this function. Yeah. So you have this sort of a general formula, this general way to find, basically if you put C high enough for any polynomial function, you can just take K equal to 1, and those are sufficient as witnesses. That doesn't guarantee that 0 is less than or equal to f of x. Yeah. Well, we're making some assumptions here. So I didn't really touch on that 0 is less than or equal to f of x, because really in the functions that we're going to analyze, so algorithms, you're not going to have any negative. You can't have a negative number of memory accesses, right? So sort of implicitly, these functions are all greater than or equal to 0. So yeah, I've sort of skipped that part because none of the functions that we're working with, for the functions that we're working with, that's not going to be a problem. Yeah, if the function is less than 0, then I would have to think about that and get back to you. Not really. Yeah, I'll get back to you. I'll think about that. I'll find out for next class. I don't think. I'm not sure if you can do big O notation. So if, for instance, your first a of n here was a negative number, then this function is going to actually go in the opposite direction. It's going to get less and less as time goes on. So in terms of computer science, that's not really that's not the domain that we're going to be dealing with. But I'll find out for you exactly what that means for big O. I'm not sure. I don't know. Maybe one of you is familiar with it, but yeah. So yeah, I've sort of skipped that because negative functions don't really apply to our algorithms that we're looking at. All right. Any other questions? All right. So we'll look at a few more examples. And then we'll end up stopping partway through this this big O notation, and we'll continue next time. But we'll get through the big O, and then maybe we'll stop at the big omega. All right, so let's take a function. F of x is the sum of the first x integers. You know, it's funny, I think somebody last semester asked me that same thing about negative functions. So yeah, I'll find it for you. F of x is the sum of the first x integers. All right, so we've seen this before. So f of x is equal to 1 plus 2 plus 3 plus x. And we know a closed form for that, but let's analyze that a little bit differently this time. So we could say that this is less than or equal to x plus x plus x, right? And this is actually x times. So that's equal to x squared. So then for c equal to 1 and k equal to 1, f of x is O of x squared, right? So, and this agrees with the closed form that we know. So this is actually equal to x times x plus 1 over 2, which is x squared plus x So this is, we can analyze it, x squared over 2 plus x over 2, which is less than or equal to, x squared for all x greater than or equal to 1. So it's big O of x squared in the closed form and in this analysis as well. So we can take even sort of these irregular functions that are not expressed in a closed form and find a big O notation for them. What about function of x factorial? So what is that big O of? Well, this is 1 times 2 times 3 times x. Maybe x is not the best. Let's use a capital X. And that's less than or equal to x times x times x x times. So this is x to the power x. So x factorial is big O of x to the power x. Right? So it's actually a very very fast-growing function that we can upper bound by this. Again, with c equal to 1 and k equal to 1. Okay, we'll do a couple more here. Any questions? All right. So what about the function log of n factorial? So we know that x factorial, x factorial is big O of x to the power x. So we could say this is less than or equal to log of x to the power x, which is equal to log x plus log x plus x times. So that's if I take, so this is if I take a log of a times b, that's equal to log of a plus log of b, right? So this expands out to this expression, which is just x log x. So then, yeah. So log of x factorial is big O of x log x. Again, with c equal to 1 and k equal to 1. All right. So these are sort of, you don't run into them that frequently, but you do see them sometimes, and you should understand how they're derived. What about log f of x equals log of x? So if we want to show that that's big O of n, so we want to show that the log of x, sorry, I keep mixing this. The log of x is the big O of x. So how we're going to show this is we're going to show that, let's just clear some space. So this is going to come up in your assignment. So this log of n is actually, or log, let's go with n since I keep switching to that. F of n equals log of n. And we're going to show that that's big O of n. So how we're going to do that is we're going to say that, well, n is less than 2 to the power n for all n greater than or equal to 1. And we can prove this by induction. So the base case is n equal to 1, and we have 1 is less than or equal to 2 to the power 1, which is true. So now our inductive case. We want to show that k being less than 2 to the k implies that k plus 1 is less than 2 to the k plus 1. All right, so our assumption then is k is less than 2 to the power k. And then we can multiply both sides by 2. So 2 times k is less than 2 to the power k. That's math. Both sides by 2. And then, so k plus k is less than 2 to the power k. That's just expressed a little bit differently. So k plus 1 is less than k plus k is less than 2 to the k, less than or equal to, for all k greater than or equal to 1. Sorry, this was supposed to be 2 times 2 to the k. And that gives us 2 to the k plus 1 over here. Okay, so I multiplied both sides by 2, or I was supposed to have. So now I have this expression, and that's k plus 1 is less than 2 to the power of k plus 1. So I've shown what I wanted to show, so yeah. So therefore, n is less than 2 to the power n. So now we're going to use this in our proof of this. So if we take the logarithm of both sides of this, we get log n is less than log of base 2 of 2 to the n, which means log n is less than n. And so then that's basically it. We've shown that for c equal to 1, k equal to 1, log n is big O of n. Okay. Any questions? All right. So we've seen upper bounds. I'm going to show you, and of course we know that the base of the logarithm is how did I get log n is less than or n? Yeah. So I proved that n is less than 2 to the power n. And then I took the logarithm of both sides. So yeah, if I wanted to get more formal here, I would say I take this fact, and then here, take log of both sides, and specifically log base 2. And then log base 2 of 2 to the power n is actually, this is equal to n. So then I get this log n is less than n. So then my constant here is just 1. Yeah, log n, that, yes, log n is less than n log, yeah, let's do it that way then. So you're saying this, why didn't we do this? N log base 2 of 2. So we sort of did, right? Because log base 2 of 2 is equal to 1. So that means log n is less than n. So, and this is for n greater than or equal to 1. So we chose log base 2 specifically because we were dealing with 2 to the power n. So we wanted to take a logarithm that was the inverse of this exponent, of this 2 to the power n, this exponential function, right? So this is, so we chose log base 2 specifically. Yeah, I should probably be writing those in. So that we would get back this n. Okay. We could have picked a different base, and then it would have been, it just would have been more math. We would have gotten some other constant here. So if I picked, let's say, I picked log base 10 of n is less than 2, log base 10 of 2 to the n, then I could express that as log base 10 of n is less than n times log base 10 of 2. And then this log base 10 of 2 is actually some decimal, right? It's, I don't know, 0 point something or other. So then we just get a different constant. So instead of c equals 1, you could still use c equal to 1, but you would get, you could use c equal to whatever this constant is. So even if you use a different base, yeah, yeah, we could have. We definitely could have. You're right. It just makes the things more difficult if we use a different base. It's just going to change the log base 10 of n is less than some c times n. It's going to change this c. That's all. Yes, you would have to use the change of log base. Well, you don't even have to though. This is your constant. Yeah, these are all great questions though. Any other questions? The most important takeaway, because I get this question all the time, and I'm sure I will again, but log base n is big O of n. So even though that's not a tight bound, that's something you can use, right? We've already established that it's okay to overestimate it. So you might be analyzing a function like n squared plus n log n. Show that that's O of n squared. Well, you can say that, well, this is less than or equal to n squared plus n squared, because log n is less than or equal to n for all n greater than or equal to 1. All right. So that's how we, these log functions come up in these expressions. And generally how we deal with them is we just round them up to this. Unless this is actually the highest order term, then this is actually just O of n log n. You can put the log n inside the big O notation as well. But if you have a higher order term, then you can just round this n log n up to n squared. All right. Any other questions? Okay, that's that graph again. So next lecture, I'm going to just give you the definition of this for now. So we talked about big O is an upper bound on the growth of these functions. So this is called big omega. And this forms a lower bound on these functions. So specifically, a function f of x is big omega of g of x if there exists c and k, again, greater than 0. But this time, we want some constant times g of x, and it less than or equal to f of x. So big O was f of x is less than or equal to c times g of x. This is big O. But now we want this c times g of x is less than or equal to f of x. All right, and this is, so this forms sort of a lower bound. So we're going to say that our function grows at least as fast as g of x. All right, but so I won't get into the details of that tonight. I'll just leave you with the definition, and next lecture we'll come back to that. It's very, very similar to big O, but there are a few twists, especially if you have negative terms, then you have to, it is slightly more difficult to prove big omega. Okay. But yeah, so that's it for tonight. I'll hang around for the next 10 minutes or so, answer questions. But yeah, that's it.